Hello, I'm Emma Pierson. I'm a professor of computer science at Cornell Tech in New York City, and today I'm going to be talking about conflicts and choices in designing fair algorithms. So, algorithms increasingly make a range of high-stakes decisions or guide them that really fundamentally affect our health and well-being and many other things. For example, algorithms are used to automatically screen resumes and sort of determine resume quality and thereby influence whether or not you can even get a job interview. They're used, as you may be familiar, to assess someone's sort of likelihood of paying back a loan, and that determines whether they can get a loan and how much they'll pay to get the loan. They're used to match people on online dating platforms. They're used to predict someone's health risk and thereby determine, what medical resources are used to monitor them and make sure they're doing okay. They've been used to attempt to predict whether patients are at high risk of abusing pain medications. And some patients have actually been denied pain medications on the basis of recommendations from these algorithms. And they've been used in a criminal justice setting to try and identify people who may be guilty of crimes. And in some cases, they've wrongly identified people and led to them wrongfully being accused. So the overall takeaway here is algorithms are really making critical decisions across a wide range of areas in our society. And it is critically important, therefore, that they be fair. But what does it actually mean for an algorithm to be fair? We've been debating exactly what fairness means for thousands of years, well before the advent of computers. And as you'll see, this is actually a very difficult problem to define what it means for an algorithm to be fair. And to illustrate some of the challenges we encounter, I'm going to tell you a story. And this begins in 2016, when the news organization ProPublica decides to do an investigation of whether an algorithm tries to predict someone's future risk of committing a crime is in fact fair, whether or not it's racially biased. So that's what they set out to investigate. So just to tell you a little bit about how this algorithm works, the algorithm is known as COMPAS. It attempts to predict someone's risk of committing another crime, and it's used to help judges make bail and sentencing decisions. So when a defendant comes before the judge, the algorithm assigns the defendant a score, which ranges from 1 to 10, and the score attempts to capture how likely that person is to commit another crime. Scores of 1 to 4 indicate that the person is low risk. Higher scores indicate that the algorithm thinks that they're higher risk. Importantly, and this is relevant because ProPublica is investigating racial bias, the algorithm does not use a defendant's race to make this prediction. To do so would, in fact, be illegal. Rather, it uses a whole bunch of other features about the defendant, like their prior criminal history, for example. So is this algorithm fair? ProPublica does a statistical analysis of the algorithm, and they conclude that the algorithm is not fair. And let's look at some of the evidence they use to conclude this. The first observation that they make is that Black defendants are more likely than white defendants to be classified as high risk by the algorithm. So a higher fraction of Black defendants are classified as high risk. And this is a violation of a fairness principle known as statistical parity. But intuitively, right, we can think of situations where statistical parity might not actually be something that we need for an algorithm to be fair. For example, consider an algorithm which is designed to predict whether someone is at high risk of breast cancer. It would be strange to say we want the algorithm to classify an equal fraction of men and women as having high risk of breast cancer, because in fact the true risks differ across those groups. So it may not always make sense to enforce this fairness constraint, to say that an algorithm must classify equal fractions of people as high risk across groups. But ProPublica makes a second and more concerning observation, more concerning to most people the first time they learn about this story. They say, look, even if you look just at the people, just at the defendants, who do not in fact commit another crime, Black defendants in this group are more likely than white defendants to be classified as high risk. So if you take a Black defendant and a white defendant, both of whom don't commit another crime, the Black defendant is more likely to be classified as high risk by the algorithm. This is a violation of a fairness principle known as predictive equality. And intuitively, right, this seems a bit more disturbing than the first observation because, after all, the whole point of the algorithm is to predict whether someone will commit another crime. So if two people are equal in that regard, we would want the algorithm to have an equal chance of classifying them as high risk, regardless of whether they are Black or they are white. So this article comes out, written by these journalists, and it spreads very widely. It starts influencing court decision, gets a ton of press. Very bad day for the company that designed this algorithm. And in response, they have to put out a rebuttal where they defend their algorithm as fair, which in fact they do. And they point out several pieces of evidence. The first thing they say, the company's name is Northpoint, and the first thing they say is, look, the algorithm doesn't use race at all. It doesn't use race to make its predictions. And this is a fairness principle, which is known as fairness through blindness. Now, intuitively, this by itself is not a very strong guarantee that an algorithm is fair. And the reason is that in a racially biased society, many, many other things end up correlated with race. So even if you don't give the algorithm race, it might implicitly sort of figure it out by using these other features which are correlated with race. For example, if you give an algorithm a person's zip code and it makes predictions on the basis of zip code, it may essentially end up making predictions that are strongly correlated with race because zip code is correlated with race. So this sort of algorithmic redlining can kind of effectively reconstruct race, even if the algorithm isn't given that. So the mere fact that an algorithm does not use race is no guarantee that it won't essentially reconstruct it by using features that are strongly predictive of race. But Northpoint makes a second observation, and they say, look, guys, if you look at Black defendants and white defendants who get the same score from the algorithm, both of those people are equally likely to commit another crime. So for example, if we compare, a Black defendant with a 6 and a white defendant with a 6 from the algorithm, both of them are equally likely to commit another crime. This is a fairness principle known as calibration. And, intuitively, this is quite an important property for an algorithm to satisfy, because imagine that it didn't satisfy it. Imagine that Black defendants who got a 6 were as likely to reoffend as white defendants who got a 4. Then you would have judges treating defendants differently because their scores from the algorithm were different, even though they were in fact equally likely to commit another crime. And so this intuitively feels quite unfair. Okay, so now we have a list of 4 fairness principles. And if you're like most people at this point, you're probably a little confused about which you think is best, but maybe you think predictive equality and calibration are particularly compelling definitions. But turns out things are about to get even more complicated, as they often do when academic researchers enter the fray. They make things sort of more complicated and difficult. And the way they do so in this case is by proving mathematically that it is actually impossible to satisfy all these definitions of fairness at the same time. Maybe you said like, oh, let's try and build an algorithm that satisfies all these things. Actually, you cannot do that in the general case. For example, in general, you cannot have an algorithm which is both calibrated, Northpoint's fairness requirement, and satisfies predictive equality, ProPublica's fairness requirement. So even though both those definitions are quite compelling, you cannot achieve both of them at the same time, except in very rare and unrealistic cases that do not apply here. So to summarize, there are many definitions of fairness. Beyond the 4 I've told you here, there are many others as well, which cannot be achieved simultaneously. And this is not a property of AI algorithms. This is a property of decision-making in general. So these fairness definitions cannot be achieved simultaneously by AI, by humans, by Solomon the Wise, not by anyone. This is an inherent property of mathematical decision-making. The trade-offs are unavoidable. Okay, so this is frustrating. So what then do we do? A couple implications of these fundamental results. The first is you shouldn't give up on an algorithm just because it doesn't satisfy some particular definition of fairness. Rather, you should think about what definition of fairness actually makes sense in the setting you are considering. You should ask yourself what definition is actually relevant to improving people's lives in the actual decision you're trying to make. There is no universal master definition of fairness. This is a highly problem-specific thing, and really understanding what makes sense requires talking to affected communities, requires talking to domain experts in these areas to understand what decisions are being made, how does the algorithm influence those, and what sorts of fairness properties do we really care about in a practical way. You should also remember that the problems I pointed out are not specific to algorithms. They apply to all decision makers. So these problems by themselves are not a reason to not use algorithms in decision making. When trying to evaluate how you should make a decision, you should always compare the algorithms to the human baseline. And remember that humans are flawed as well. It's not like humans are, automatically perfectly unbiased decision makers, as we all know. Finally, to close, while I've told you some difficulties in designing fair algorithms, these are by no means the only difficulties. There are many other challenges as well. So this remains a very difficult open problem. How do we actually design algorithms which are fair? But in spite of this, I think there is twisted cause for hope. Specifically, people in many ways are even worse. And so this is one reason that in spite of all the challenges, I remain an optimist about the ability of algorithms to improve equitable decision-making. If you want to dive deeper on this topic, I've included some links and further reading, and you can learn more about this topic here. Thanks very much.